Yeah. So in this session we will be discussing colligative properties. So one of the very important topic of solutions chapter right now. So what exactly colligative properties? Yeah. So what exactly colligative properties? So these colligative properties, if you observe, we have many daily life applications also. Like for example, if you want to elevate the boiling point of water, for example, we are cooking something, let us say we are cooking for rice, okay. So when we are making rice, what we'll do, we'll use water right now. So in order to increase the boiling point of water, for example, rice is not cooking properly, so that some of our parents might add some salt to it right now. So why they will add salt? So by the addition of this salt, the boiling point of water is elevated. Previously it will boil at 100 degrees now the boiling point of water will be elevated to some other temperature like 102 or 101 based on the amount of that salt added to it, okay. So why? Because this is an application of colligative property, especially we can study it as elevation in boiling point, okay. So now we are going to study about that kind of things here. So what exactly colligative properties means, just look at here. So these are the special properties, or these are the properties of dilute solutions. Dilute solutions, I can also say them as dilute solutions, or especially if I want to mention, it is the properties of ideal solutions. We have discussed about ideal, non-ideal solutions in the last class right now. So these colligative properties are the properties of ideal solutions. So now what exactly it is? So here it is the number dependent properties. Number dependent properties, it means what? Dependent properties. So what exactly this number dependent properties means? For example, number dependent properties means it is irrespective of what is the nature of solute present in it. It depends only of number of particles present in it. It depends only on these properties. I will explain you, just wait for some time. These properties depends only on number of particles. Here I am saying solute particles present in it, irrespective of nature of it, irrespective of nature of that solution or the solute particles, that depends only number of solute particles present in it, okay. So now for example I am saying here, just now I have told you to elevate the boiling point of water. Now they can add some salt, NaCl. Now what happens, its boiling point is elevated from 100 degrees to some 101 or 102, okay. So here what exactly here I can say is the colligative properties of KCl and NaCl is similar. I am writing. Why I am saying these are similar? See how many particles it can give. It can give one K plus ion and one Cl minus ion. Now, so number of particles becomes how many? Here it is 2. Now in this case, how many particles we are getting? So Na plus one particle and Cl minus other particle. So here also it is giving 2 particles now. So the colligative properties of these two substances are almost same, okay. So that is what you can understand. Now if I add same amount of KCl, for example I am adding same amount of KCl and glucose, will the change in their properties seems to be same or not? No, here because in the KCl how many particles we have? Here it has 2 particles and here glucose is non-electrolyte now, so there is no dissociation of ions from the glucose right now. However, its molecular weight is greater but it won't dissociate. Therefore what happens, I can say it has only one particle, that complete molecule be considered as one particle, whereas KCl upon addition to the water, what happens? Dissociates to K plus Cl minus, na, giving 2 ions, whereas here only 1 ion. So colligative properties here in this case will be different. Now what are the types we have? How many types of colligative properties? I am writing types of colligative properties, types. Okay, so first one is relative lowering of vapor pressure. So you can write as RLVP, means relative lowering of vapor pressure. Okay, and the next, second one is elevation in boiling point. I am writing EBPT, elevation in boiling point indicated with delta TB. Okay, and next, third one we have depression in freezing point, DFPT, delta TF. Okay, and fourth one we have is osmotic pressure. Okay, so osmotic pressure I am indicating with symbol pi. Okay, these are the things we have as colligative properties. Now we need to discuss one by one. From any of these you may get one question. Okay, see now here, yes, I am looking into the chat box, you can write, I will be looking it. Okay, yeah, hello dear, hello. So now if you have any concerns, you mention there. Simply we can't discuss anything, right? Yeah, so now what I told, all these are colligative properties. So these are what? Number dependent properties, number of particles. If more, colligative properties also rises, they will also become more. Okay, so they increases with number of particles as they increase. So here there is a term called Van Hoff factor I will be discussing about it in the upcoming sessions. Okay, so as I value increases, all these colligative properties also increases. I will tell you about this I value, that is what Van Hoff factor, in the upcoming sessions. Just now just focus and just get some idea over these 4 topics first. Okay, let me write the first heading as RLVP, relative lowering of vapor pressure. See, how can you understand this in a better way? See, I have a solvent, I am indicating with A, solvent A, and I am saying this is volatile solvent. What I am saying? Volatile solvent, and vapor pressure of this volatile solvent I am saying it as P0A. Okay, listen here, it will be very easy to understand. P0A. Okay, so I am having a beaker containing this component, this liquid, this volatile liquid in a closed jar, let us say. Okay, so what we have here, this is A, component A. Okay, in the liquid phase. Since I told you this as a volatile one, what happens? Some of this compound will be converted into its vapors right now, and we know there exists an equilibrium between vapors and the liquid of this volatile component A right now. So now to this volatile component I am adding non-volatile solute. In order to make a solution, what we have? Solute and solvent, both we have now. So in order to make a solution, I have a non-volatile solvent, volatile solvent, to that I am adding non-volatile solute. So what happens? We know volatile solute I am representing with symbol B. Okay, so vapor pressure of this component as P0B. So we know, since it is non-volatile, it doesn't express or doesn't show vapor pressure now. So I am considering P0B is almost equals to 0. Okay, so now vapor pressure of this non-volatile solute is almost equals to 0, I am saying. So whenever we add this non-volatile solute to this solvent into this beaker, what happens to the vapor pressure of this component? Decreases, right? Because it is non-volatile, it is volatile. What happens? It is converting into its vapors and exerting vapor pressure. Therefore it has high vapor pressure. But when I add this to this component, just look, let us take this beaker once again. So to this, what I am adding now? So in this case I am adding some amount of this non-volatile component. So what happens? This component, B components will be indicated with symbol. Let us say I am using this red color to indicate this B. Now what happens, this non-volatile particles appears on the surface now. So now what they will do, they will be like acting as a like hindrance, right? Now the escaping tendency of vapors of these volatile components will be decreases now. Therefore what happens, the vapor pressure of this solvent decreases. So what RLVP says, the vapor, look at here, when a non-volatile component, when a non-volatile solute is added to volatile solvent, its vapor pressure decreases. Which vapor pressure decreases? Vapor pressure of volatile solvent decreases. So its vapor pressure decreases. Hope it is clear. Why it is decreases? Because the solute particles can have like act as a hindrance to the vapors of this volatile component A and makes them to have low tendency to escape, right? Now therefore vapor pressure of the solvent becomes less. This is what you need to understand here. Hope this is also clear now. Yes, if any confusion, they just ask me. So now I told you that P naught A is a vapor pressure of this component A. Now here I am saying this is a solution now. See, A is added, B is added to A, so we got a solution here. Now what we have here, we have A and this red color is B, right? Now so it is a solution. So now for this solution I am saying PS is a vapor pressure of solution, or P total also we can say. Okay, so now total pressure, total vapor pressure, I can say P total, PT or PS, that is total vapor pressure of solution. PS is equals to what? According to Raoult's law, what we have studied, P total equals to PA plus PB, right? Now what is this PA? PA is a vapor pressure of A in this mixture. Okay, so I can write this as P naught A and XA plus this as P naught B XB, right? This is equals to PS. Hope it is clear up to here. But what we know, since volatile solute we have, its vapor pressure is 0. So it means this value is 0, means overall term becomes 0. So PS vapor pressure of solution is equals to P naught A vapor pressure of pure solvent multiplied with its mole fraction, right? Now so this is what we got a final equation up to here. Let me think about it again. See, we have sum of mole fractions. What I can write? Mole fraction of A, since solution is made up of two things, A component A, B, binary solution now. So sum of mole fractions of A and B is equals to 1. So from this, here in the place of this XA, I can write 1 minus XB. Yes, you can substitute this in this equation, you will get PS equals to P naught A into 1 minus XB, right? Okay, so just multiply that and what we'll get? Yeah, so PS equals to P naught A minus XB into P naught A. Okay, next here if you observe what is P naught A, it is a vapor pressure of pure solvent, right? Now so from that I am writing P naught A XB equals to P naught A minus PS. So if you observe this, P naught A is a vapor pressure of pure solvent. Now this value is lowered by PS, right? Now so this is the term called as, this equation is called lowering of vapor pressure, LVP I am saying, lowering of vapor pressure. See, vapor pressure of solvent is lowered now. Yeah, that is what I am writing here, lowering in vapor pressure I can say. Okay, so now the name of this concept I have mentioned it as relative lowering of vapor pressure, right? Now so what exactly relative lowering? Relative means when we relate to the initial one and this final one, we can say relative lowering. So initial one is nothing but P naught A only now. So I am writing XB equals to, this mole fraction of solute B is equals to P naught A minus PS by this P naught A here, right? Now see, relating to the initial vapor pressure of solvent with the final vapor pressure after mixing, that is what relating lowering of vapor pressure we got. So this is the equation. See, RLVP, relative lowering of vapor pressure of that solution will be equals to mole fraction of solute. What is the final equation you got RLVP equals to relative lowering of RLVP equals to relative lowering of vapor pressure equals to mole fraction of solute present in that solution. That non-volatile solute, whatever the amount we have in terms of its mole fraction, that will be its relative lowering of vapor pressure. This is the main equation you can remember here. Okay, so now let us solve one or two questions on these to make it more clear with the concept. Okay, so I have a question for you. So just read this question once. Just look at this question. Mole, the one mole of non-volatile solute, the final equation that we got is a main equation. What we got? Mole fraction or RLVP. Here we have now RLVP is equals to P naught A minus PS by P naught A. This is what we got now, which is equals to mole fraction of solute. This is a main equation you need to remember. So what is P naught A here? Vapor pressure of pure solvent. PS means vapor pressure of solution. Again P naught A, vapor pressure of pure solvent. XB means mole fraction of solute, whereas XA means mole fraction of solvent, right? Okay, now read the question. 1 mole of a non-volatile solute is dissolved in 2 moles of water. Okay, the vapor pressure of solution, it means P vapor pressure of solution relative to the vapor pressure of water. It means PS relative, they are saying PS to P naught A. So what is our solvent here? So solvent is water, solute is some 1 mole of solute they are saying. So they haven't mentioned what particularly solute is. Let us say some solute B is there, and what is our solvent? Water. So to the water solvent, B solute is added in order to make a solution. Okay, so what is a relative vapor pressure of the solution? See, they are asking the vapor pressure of solution relative to water. So this is what they are asking. Okay, try to understand the line they are asking us. Okay, they are not asking relative lowering of vapor pressure, they are not asking RLVP, they are asking this ratio. So how do we get this ratio? Just look at this. We have RLVP as P naught A minus PS by P naught A, which is equals to mole fraction of B. Okay, so we required this term now. This term is nothing but, see, I can write this equation as P naught A by P naught A minus PS by P naught A, right now, and this is mole fraction of solute. So this will be 1 minus PS by P naught A, which is equals to chi B. So from this what I can write? So I can send this that side and we'll get something like 1 minus chi B will be equals to PS by P naught A. So we got this now. Yeah, this is the term they are asking. Now what about this mole fraction of solute? How can we get this? So look at the data. They mentioned number of moles of solute NB equals to 1, and whereas number of moles of water mentioned as 2 moles right now. So total number of moles 2 plus 1 becomes 3. So mole fraction of solute, chi B means solute now, XB means that is number of moles of solute by total number of moles, NB by N total. Okay, so from this what will get? NB XB equals to 1 by 3 right now, 1 by 3 I am writing here. So in the place of this mole fraction of B, right, 1 minus 1 by 3 equals to PS by P naught A. Okay, so try to simplify this. 3 minus 1, it will be 2 by 3, 2, 3, like this LCM you do, you will get 3, 3 into 1, 3 minus 1, 2 by 3. This is the value of PS by P naught A. Yes, now, so this is your answer. So check for the options. Yes, so we have somewhere 2 by 3, first option we have, yeah, that will be our answer. Hope it is clear. And you know why I have made this many steps? You can do within 1 or 2 steps, but you know most of the people will confuse with this term, vapor pressure of solution relative to the water. It means that it doesn't mean that RLVP, it means what? Vapor pressure of solution to the pure solvent. Okay, so this is the initial like basic kind of questions you need to focus first whenever you are preparing. Okay, whenever you are studying this concept. Okay, so now you have listened to this. Now you just, after the session, you just give a try for solving the questions based on this RLVP. Okay, now I have one more question based on this RLVP. Just give me some time, I will be writing it. Yeah. See, a set of solutions, write the question, a set of solutions, a set of solutions is prepared by using 180 grams of water. 180 grams of water. Very easy. Question seems to be very large, but just listen here, you will get the answer. Water as solvent and 10 grams of different non-volatile solutes, like solutes like A, B and C. Okay, the RLVP, relative lowering of vapor pressure in presence of these solutes are in the order of what? So they will be asking RLVP is more for which one, like RLVP is more for which one. They are asking either A is greater than C is greater than B, or A is greater than B is greater than C, something like they are asking. Okay, we need to arrange them based on these orders. Okay, so now how can we arrange them? Just look here. They also given data also contains molecular weight of A or molar mass of A is 100 gram per mole, and for B is 200 gram per mole, for C 10,000 gram per mole. Very easy, just look at its data and formula and try to understand the question. A set of solution is prepared. See, this is a JEE mains question, previously asked question. Okay, a set of solutions is prepared by using 180 grams of water as solvent and 10 grams of different volatile solute. Okay, ABC. The RLVP in presence of these solutes are in the order. So how can we give? So write the RLVP formula first. RLVP, I can write RLVP equals to, I am directly writing mole fraction of B right now. Why? Because they are talking in terms of weights and all. No? So what is our solvent and solutes here? Solvent is mentioned as water. Okay, that is fixed for everyone. So now they have taken water as a solvent and they made 3 solutions using solute A as one solution, solute B and another solution, solute C as another solution, like this. Okay, now they are asking RLVP order. So this XB I can write NB by N total right now. Yeah, so N total again I can write in terms of Na plus Nb, right? So here Na, number of moles of solute, Na is how much it is? See, Na is how much? So number given weight is 180 grams and its molar mass is how much? Its molar mass is 18. So this will be 10. Okay, so Na will be 10 moles, whereas Nb will be something different here. So Nb will plays a crucial role over there. Okay, so Nb means I can write weight of B, means given weight and molar mass of that B, solvent B. Okay, so here B doesn't mean this B, all ABCs. Okay, into Na plus Nb. So now see how RLVP related to its molecular weight. It is inversely proportional now. So take 10 grams everywhere by molar mass is changing. First case for A it is n number of moles of A is like 0.1. For B will be 10 by 200 means it is 1 by 20, and for NC will be very high, 10 by 10,000. This is 1 by 1000. So now see where do we have? So number of moles here, if you see, it is very less now. See, it is very less. So I can say as molecular weight is larger, since weight is same in all the cases, so you just relate this mole fraction is inversely proportional to its molecular weight. That's it. Right now, if mole fraction is inversely proportional here, I mean just for getting conclusion I am saying. So RLVP definitely inversely proportional to this molecular weight now. So RLVP, instead of saying here mole fraction, I can write RLVP inversely proportional to mole fraction of molecular weight of solute. Okay, so which is having larger molecular weight C now, so it will be having lower vapor pressure, lower relative RLVP. So I can say RLVP order as so C is least, after that B is more than A, so after that B, and highest is for A. So why? Lower molecular weight, greater will be its RLVP. That's it. This is the concept you need to use to answer this kind of questions. Okay. So now basic two models which are very required to solve questions I have explained. Now you can solve few more questions, and any question is there to be discussed, you can post in my Telegram channel, in our this NEET World's Telegram channel, so that I will help you if you are unable to do those questions. Okay, I will be there. I will be helping in through that channel. Okay, you can join and access our free sources. Okay, thank you for watching.